So all of the hypothesis testing we were doing was for a single idea or a comparison of two means. What if I have more things? Or what if I have more contributing factors to a given outcome? Well, what we can really do is what's called analysis of variance, more oftenly abbreviated ANOVA. And really what we want to do is we want to do these mean comparisons, like say I have 4 or 5 of them. I want to do them all at the same time rather than trying to do, okay, let's look at mean 1 and mean 2, mean 1 and mean 3, mean 1 and mean 4, mean 1 and mean 5. If I wanted to do it that way, there'd be 10 different tests. That's disgusting. I'd like to do it in one fell swoop, if possible. Now, it's important to have good experimental design, good questions, and good ideas of what pieces contribute to the answer in my question in order to get the best possible relationship between what's going on. So let me set the stage as if we were doing an algebra problem. There's a dependent variable, y, our output. We're also often going to call this the response variable. And there'll be several different inputs. The independent variables however many we have. And these could be numerical, they could be categorical. They don't have to just be numbers. Sometimes called the factors or the explanatory variables, the things that explain variation get out of if we change x to whatever, what changes does that cause in y? Now, in algebra, you've got a formula. I put in this x, I put in this x1, this x2, what changes in y? But in this setting, I'm looking at a mean, a standard deviation, a proportion. I'm going, well, if these things are changeable, what could be the reason? And variation in y can be caused in two different ways. It could be in the factors. So whatever variation happens in y could come because something is varying in x. Like we have a large standard deviation. Or it could be random error. And if the factors are explaining explanatory variables, then our random error is otherwise unexplained error. So I don't know how much you did in your algebra class about graphs of more than one variable. But I'm going to make something up right at the moment. I just made up a function of two variables. Now, I'm pretty sure in my algebra class, I would have written this as f of x and y. But I don't want to use x and y. I want to think of y as the output. So I'm going to call this equal to y. And now if you change x1, then you change the value of y by a multiple of 2 times however much you changed x1. If you change x2, you change y by 3 times however much you changed x2. If you change both of them at the same time, you get a combined amount of change. Make sense? Some of you are nodding. Some of you are staring at me like I'm a space alien. A way to think of this visually. When we graph a function of x, we have an x-axis and a y-axis, right? Now I've got 2 x's. So what if I drew them on the table in front of you? And then let my y value go up in the air from that. I would have a 3-dimensional picture. Picture me standing in this corner at the origin, just like I'm standing in the corner of the room. And the x1 axis points out in front of me. The x2 axis points off to my left. The y-axis goes out the top of my head. Point your finger at me. Stick your middle finger out to the side. Don't point it up. Stick your thumb up. There's your 3-dimensional axis setting. Right there. You carry it with you everywhere you go. But be careful. This is set up right-handed, not left. You go to use your left hand and try and make it match, you're going to have to do this, and that's rude. Don't do that. Right-handed. But since I can have as many explanatory variables as I want, I can think of this not just as 3-dimensional, but maybe 4-dimensional or 5-dimensional, at which point the pictures get away from me. But the foundational idea is the same. All of my x's get to change. What happens to my y value? Okay. ANOVA is a comparison of means. I'm going to look at the means in my explanatory variables, how they affect the mean in the response variable. And I'm going to look at all the possible variations in the factors and combinations of different factors. That's called a treatment. And what I want to test is whether each factor has a major effect on y. I can also test to see if each factor influences some of the other factors. Now, in order for me to do the test between factors. I am testing variances. We just finished on Friday testing variances. What test and what distribution did we use to test for variances? I use my F distribution, Fisher's distribution. So I'm going to use the F test here. And that means that I'll do some F critical value. The more factors I have, the more complicated and difficult these tests get. I don't want to use dozens of factors. That's going to be very expensive to try and say, oh, I've got all these 15, 20 different things. How do they affect each other? That's going to be really problematic, especially because some of those items might be directly related. As I mentioned earlier in the semester, I have been working on this data analytics paper in volleyball. And one of the things that was specifically examined was the relationship between digs and blocks. Wait a minute, isn't a dig a type of a block? Oops, it's going to be counted in two places. I can't do that. Those factors are going to be very much influencing each other. So I don't want to use both of them in a model, do I? So while I can use lots of factors, we more often count on small numbers of factors, maybe 3 or 4 at most. The more factors we include, the harder and more complex these models get. I'm going to try and avoid that. So let's pull an example and let's talk about what sort of hypothesis we would be testing as we examine this. So we have the CHIPS program designed to bring home to America modern semiconductor technology. We are making more chips for computers and phones and cars and all electronics here in America. What happens? I look at 4 different plants manufacturing automotive computer chips. And I look at, over a couple days, I look at what the defect rate is at each plant. And here, at the bottom of page 411, is a dot plot of 4 different plants, A, B, C, and D, and their defect per 1,000 chips. So 2.8, 2.2, 2.4, etc. Is there enough of a difference between any of these plants that can be attributed to something other than randomness? Is defect rate higher at one versus the others? So the factor in this problem is which plant am I at? But I'm comparing 4 different averages, not 1 or 2. So my hypothesis test needs to be set up differently. So I need a null hypothesis and an alternate hypothesis. I'm going to try and do the same sort of thing we were doing last chapter. If I've got 2 things, the null hypothesis was that they were equal. And then the two-tailed test was they weren't equal. Well, now I've got 4 different means. And I'm going to say my null hypothesis is that all of the mean defect rates should be the same. There really should be no difference of behavior at any of the plants. There's nothing special about working at plant A or plant C or B or D that makes you have more or less defects. It should be the same. Production behavior is the same. The production line is the same. I'm putting people in the same jobs. It should be exactly the same thing. If that's my null hypothesis, what's my alternate hypothesis? Say again? Well, not necessarily everything doesn't equal everything, but at least one of them could be different, right? So I'm just going to say they're not all equal. It could be that 3 of the 4 are equal and there's one crazy place. It could be that 2 of the 4 are equal and 2 of the 4 are very different, not just from the other 2, but from each other as well. There's some sort of variation going on here. And then my y, my dependent variable, is the defect rate. And my factor is which location am I at? Notice that's a categorical variable. It's not a numerical variable. It's just, oh, I've got a location to consider. Okay. Questions so far? I haven't even set up the problem or anything like that yet. Okay. On page 412, there's something about the same idea about hospital stays. Do people stay longer at one hospital location than another? UPMC has a gazillion different hospitals. Does one of them do longer stays on average than the other? Automotive painting and paint quality and what temperature that paint needs to cure at could be, again, dependent on what kind of paint, what quality do I get out? Are all things I want to say, well, no, the temperature at which we cure at doesn't matter. Maybe it does. Questions? I need to make some assumptions about the variables themselves. In order to minimize the bias I am creating, I want to have independent observations on my response variable. I also want to assume that all of the populations involved are normally distributed. And I also, for right now, I'm going to assume all my populations have equal variance. Now, this is a case where I guarantee you doing this by hand is off the table. It is not reasonable to do the number of distinct calculations we are going to need to do by hand. All of this always gets done in Excel. Which means I'm going to pull up an Excel sheet and go through an example, and they're going to do all the work, and I just have to understand what the hell is going on, know how to read the output. But I want to explain at least a little bit of how we get this model and how we get the reason it's better to do this than to do a bunch of different t-tests, right? Like I said, if I only had 2 factors, well, look, we had 4 in this, right? I got 4 different treatments, 4 different plants for my chip manufacturing. I could test mean 1 against mean 2, mean 2 against, mean 1 against mean 3, mean 1 against mean 4, mean 2 against mean 4, mean 2 against mean 3, and mean 3 against, I could do 6 different t-tests. We already know how to do that. Why don't we do that? Because the errors get to be problematic. So, if we are only interested in comparing means, on some number of groups, C. I don't know what C is, but it's the number of groups I've got. For our chip example, that's 4. Those are our 4 treatments. Then I'm really doing what's called a 1-factor ANOVA. So I start pulling chips, right? I take chips from plant 1, I take chips from plant 2, chips from plant 3, and so on. But I didn't particularly make up these assignments out of nowhere. They're randomly selected within each group. We call that a randomized model. So since I'm not saying that there's any relationship between these 1,000 chips and the next 1,000 chips, I just pulled this from plant A and this from plant C, completely at random. That's a randomized model. So I go to the first factor and I pull a bunch of samples and I get my numbers. Now we took, in our dot plot, we had 10 different lots of 1,000 chips. We measured the defects per 1,000 in our lots, and we wrote a dot for each one. So, on page 414, there's a couple of tables about the way in which we create the data. So, in this setup, each treatment is a column. These observations all come from treatment 1. So notice Y11 is the first row in the first column. Y12, first row in the second column. All the way over here to Y1C, the first row in the Cth column. There were C different groups. For us, it was 4. So I'd have Y11, Y12, Y13, and Y14. And in that first first column, I'm going to have however many observations, N1 observations, and there's going to be an average for those. Same thing in the second column and the third column and all the way up to the Cth column. So each column gets an average and has its own number of observations. They aren't necessarily all the same. I could do them in columns, I could do them in rows. Notice when I do the row changing, the subscript behavior changes. In the first row, all the treatments, Y11, Y21, the second number tells me that I'm going with treatment 1. The second number told me I was going with treatment 1. The second number told me I was going with treatment 2. This makes me twitchy because I always read double subscripts as having row and column, like with the F table, and they reverse it when they switch the data around. I just learned to live with it. The second number is the treatment number. Which factor are we in? I don't care whether you lay your data out in rows or columns. You just need to keep it straight so that you can tell Excel which way to do the test. Now, I get a bunch of different averages, right? Each average is computed and then compared to a group average. So I take all of the total observations, N1 and N2, all the way up to NC for each group. I can add them all up to get one big N. So I make a bunch of observations. Now, it would be nice if all of the N's were equal. If I made just as many observations in treatment 1 as I did in treatment 2, that balances my behavior better, but it's not a requirement. Instead of doing C, however many different t-tests I'm going to need. Remember, when we do a t-test, there's a confidence level, right? There's that alpha for precision. Well, let's say I did alpha's 0.05. Well, that means that there's a 0.95 chance I got it right and a 0.05 chance I didn't. My sensitivity. Well, in that case, every time I do another t-test, I multiply that together. Do me a favor, grab your calculators. What's 0.95 raised to the 6th power? Take 1 minus that, because 0.95, remember, chance I make an error is 5%. 1 minus that is, so all of a sudden, instead of having a 5% error chance, I have a 26% error chance. Oh boy. The more t-tests I do, the bigger that error gets. If I do 5 groups, then the chance my error gets all the way up to 40%, even though I'm doing alphas 5%. compounding error, like compound interest, these numbers get big really quickly. ANOVA gets around that. We do one test. Now, that one test kind of acts like my equation earlier. Y equals 2x1 plus 3x2, right? So I can think of my Y value as having effects by all of these treatments. So I can say, oh, my Y should somehow have an average that is then affected by my treatment and maybe some unexplained error. And my goal is to figure out what this average is based on these two relational behaviors. There should be an I over here with the Y. My hope is that I can look at this and I say, okay, this variation, this error is attributable to these factors. This random error, I don't know where it came from. Everything you do, every sample you take has some layer of error, but I can assume that this random error has a mean of 0 and is normally distributed. So on average, that epsilon should be very, very small. My original null hypothesis. My original null hypothesis was what? All my means are the same, right? If all my means are the same, then this should be 0. Oh, so another way to think of my hypothesis is to say, oh, what I really want to check is whether or not these are causing any change. Is there variation I can find due to these factors? So another version of my null hypothesis is that all the TIs are 0. Usually this is referred to as a fixed effect model. Fixed effects model. Now, there are two different kinds of variation that show up. There's the variation within the group. I looked at chips from plant A. There's some variation in chips from plant A. And then there's variation that happens across the groups that could be attributable to my factors. So we're going to look at two different observations, and we're going to do a whole crap ton of algebra. And what we end up with is at the bottom of page 415, and this is the only time you're going to see these abbreviations. SSB, sum of squares between. SSE, sum squared error. That's the outside within a group. This is across groups. Then we add those together and we get the total error. Notice the degrees of freedom. Still n minus 1, isn't it? But it's broken up into two groups. It's the C minus 1 with the groups, and then it's n minus C within the groups, because that's the rest of the observations. Just like with our F test, we take square and divide by square. But our F statistic is these squares. You need this number. That's the number we're going to do. I don't want to do this math by hand. I hate doing this math by hand. But at the same time, I want this picture in my head of this 3D model, right? Now, if this is the equation, that's kind of like the equation for a line, isn't it? If I'm in 3D, I don't have a line, I have a surface. A surface. As I change x1, every time I change it, we go up by 2. As I change x2, every time we change it, we go up by 3. So it's steeper this way than it is this way. So I've got this surface here. And my data will kind of be above, below, on average, it'll be on here. But some of it'll be above, some of it'll be below, kind of like a scatter plot. The scatter plot in more dimensions. So, I get an F statistic, and then I do the same thing we've done before. I find a critical F, and I look, are we above and below? I hate that version. I'm going to use the p-values. Because we'll have an alpha every time. 5%, 1%, 10%, whatever it is. I'm going to look at the p-value generated by my F. My p-value is smaller than alpha. I reject my null hypothesis. Here is the data for the first example in the text on page 417. We have number of cartons packed at a manufacturing and distribution center. The summary data appears in the upper right there, station 1, couple of five randomly selected days, produced 236, 250, 252, those are my numbers. I could drop this into a graph, and I could do the dot plot just like we were looking at with our chip issue. Not always sure that helps. But what I've got there is column-driven data. Each factor is a column. Yes? Which plant are you at? Does that affect how much you're producing? My null hypothesis is going to be the average production at every plant is the same. The data sheet in our downloads section is called cartons, and the examples in chapter 11. So I'm going to say I want to do an ANOVA test on this data right here. So I'm going to go to my data section, and I'm going to go to data analysis. Same place we were before, right? T-tests are all there. Z-test is there. If I scroll up on this list, lo and behold, the very top of that list are 3 different ANOVA tests. Which one are we doing? One factor. Single factor ANOVA. So I'm doing that very first one, ANOVA, single factor. I click on that, and it says, all right, where's your data? I'm going to tell it the data is here. Oh, yes, and I have the labels in the first row because I highlighted the labels. And it's grouped by, see how you can have selection between columns and rows right here. Mine is grouped by columns. Now, is variation among the stations within the range attributable to chance, or do these samples indicate actual differences between the averages? Okay. I think for now I'm going to deal with 5%. If I set my alpha to 0.05, which is what it is right there at the moment, I can say, please do this and generate for me all the statistics, do all of the squaring and subtracting and dividing and averaging, and give me an answer. New worksheet ply. There we go. Well, that's pretty freaking helpful. This doesn't really give me very much information at first until I figure out what it says. Just like Friday, I end up with two critically important pieces of information here. I end up with a calculated F value right here. F, 4.1217. Now, in a test with two tails, I want to know if I'm outside, right? So I either need to be bigger than the big one or smaller than the small one, but they only give me one critical value here. F crit. They are always switching from 2 to 1/2 the size. That's still the correct test. We just folded it in half, really. So compare my calculated F with my critical F. What does it tell me to do? Reject what? I should reject my null hypothesis because the calculated value is the critical value. And that's what? If I reject the null, I take the alternate. The alternate says means they're not all the same. Take a look at the top set of data. Summary. There's the averages right there. Is there a clear difference between averages based on location? Oh yeah, there are two of them in the 220 range and two of them in the 240 range. There is clearly a difference based on which station you are at. And the other way to test this, the other way to check this, is not to use the F values. Instead, use the P value. What's that P value tell me? Because it's less than 0.05. That was my sensitivity, my precision. It's less than 0.05. 0.02 is definitely smaller than that. There's only a 2% chance that this type of variation could happen randomly. There's got to be a cause for this kind of variation related to those T's we were talking about here. There's got to be some relation to the factor. It can't just be random. The chance of this happening solely randomly is very, very small. How small? That small. We said they're not all equal. That's all this test tells me. It tells you, hey, the means are not all the same. But now that I know that, I then have to go back and look at the actual averages to see where the differences occur. Which factors cause what? And in this case, with only one factor really being involved, I can say, oh, yeah, there's definitely something different in stations 1 and 2 than stations 3 and 4. Now, I have never worked a packing line in my entire adult life. So I have no idea what could be different between station 1, station 2, station 3, station 4. But it's quite reasonable to say, oh, no, there is clearly something different happening there. Depending on your problem setting, it is quite possible to have a lot of different ideas. Problem 7. Semester GPAs are compared for 7 randomly chosen students in each class at Oxford University. Accounting majors, finance majors, HR majors, marketing majors. Is there a clear difference just based on major in average GPA? Or is the variation random? Now, I can look at this data and I can go, I think there's a variation based on major. All of those marketing majors, well, most of them have better than a 3.0. And that's not, well, there are more under 2 in the accounting and the finance. Okay, wait a minute. Is it really just that different? But I could use the 4 factors: accounting, finance, HR, and marketing. And I could do the same thing, and I could ask, if I'm looking at just those majors, same data. If I run the ANOVA here, again, with 5%, 0.05 for alpha, is there a clear difference? Is there a clear difference? No. My null hypothesis would say all the means are the same, right? The average GPA is the same regardless of which of these 4 majors you're in. But I set alpha to be 0.05. What's my p-value here? 0.03. I should reject the null hypothesis. There is at least one mean that isn't the same. There's one GPA where being in that major is harder or easier. So then I go back and I look at the actual averages. And yeah, accounting has a 2.8, HR has a 3.24, marketing has a 3.37. There's a difference between these majors, isn't there? At least at Oxnard. I don't know about at Seton Hill. But there's clearly a difference between the averages. Choose a major that gives you the GPA you want. One major is easier than the other. I don't know. That seems to say so. Questions? All of this is based on the idea that there's only one categorical difference between the data I'm using. In this case, it was which major. In the previous example, it was which station. In the CHIPS example, it was which plant you were at. That's not always the case. So there are more options for an ANOVA. And we'll talk about some of those on Wednesday. Please note, I have uploaded the the information sheet about the exam. You get a new formula sheet. There's a crap ton of formulas. When I took the exam this weekend, I wrote it up and I took it. All I had in front of me was the formula tables, and every time I needed a table in the back of the book, I said, oh, you guys are going to need a table. I'm going to give you the tables. You will not need to use the F tables. I will give you the F values that are needed for any F test we are doing. Questions? I will see you all on Wednesday. Have a wonderful rest of your day. Colin, Nico, don't leave. Don't leave. I need to find out what we're doing.